What is the specific problem that the proposed method, gradient boosting reinforcement learning, GBRL, aims to solve in the context of reinforcement learning?
The specific problem that the proposed method, gradient boosting reinforcement learning, GBRL, aims to solve in the context of reinforcement learning is the limited application of traditional gradient-boosted trees, GBT, in RL due to challenges such as the dynamic nature of RL environments, distribution shifts in input and output, and the lack of benchmarks tailored for structured data. GBRL addresses these challenges by introducing a GBT framework tailored for RL, demonstrating the viability and potential of GBT as function approximators in RL, providing a tree-based actor-critic architecture to reduce memory and computational requirements, and offering a modern GBT-based RL library optimized for RL tasks. GBRL aims to leverage the strengths of GBT in handling structured and categorical data from supervised learning and transfer these benefits to the RL domain, while also addressing the unique challenges of RL, such as non-stationary state distributions and online learning.
How does the proposed method, GBRL, work? Please illustrate step-by-step the methodology used in GBRL.
The proposed method, gradient boosting reinforcement learning, GBRL, works by extending the framework of gradient boosting trees, GBT, to support actor-critic AC algorithms in the task of reinforcement learning, RL. The objective in RL is to optimize the return, the cumulative reward an agent receives through trial and error learning. In GBRL, the ensemble of decision trees grows iteratively to optimize the objective directly over the decision tree function class. At each iteration, a new tree is added to the ensemble to minimize the distance to the gradient of the objective. This is achieved by constructing trees that predict both the policy distribution over actions and the value estimate, sharing a single feature representation for both objectives to reduce memory and computational bottlenecks. GBRL leverages functional gradient ascent, where each tree in the ensemble represents a linear combination of functions parameterized by AC parameters like the policy and value function. The method adapts GBT's incremental learning strategy by fitting decision trees on random batches sampled from the experience buffer at each boosting iteration, allowing beneficial gradient directions to accumulate and minimizing detrimental ones. GBRL directly fits gradients to optimize objectives, unlike traditional GBT methods that require predefined targets, and utilizes a shared approximation for the actor and critic within the decision tree structure. This approach enables GBRL to efficiently solve complex high-dimensional RL tasks, particularly in environments characterized by structured and categorical data, showcasing its potential advantages over neural network-based approaches in certain scenarios.
What are the theoretical or practical benefits of using gradient boosting trees, GBT, in reinforcement learning compared to neural networks?
The theoretical and practical benefits of using gradient boosting trees, GBT, in reinforcement learning compared to neural networks lie in several key aspects highlighted in the paper. Firstly, GBT excels in handling structured and categorical data, making it a strong candidate for tasks involving such data types. This is crucial as many real-world applications, such as inventory management and resource allocation, involve structured observations with categorical or mixed data types. GBT's natural handling of structured and categorical data allows for more efficient and effective modeling in these scenarios. Additionally, GBT offers interpretability, which is essential for regulatory reasons and building trust in decision-making processes. Interpretability methods for GBT leverage the structure of decision trees, providing high speed, efficiency, and accuracy in interpreting model decisions. Furthermore, GBT's incremental learning strategy aligns well with reinforcement learning's trial and error learning approach. GBT's ability to fit gradients directly to optimize objectives without the need for predefined targets allows for seamless integration into reinforcement learning optimization packages. This incremental learning strategy helps handle non-stationary distributions and improves stability by accumulating beneficial gradient directions while minimizing the impact of detrimental ones. Additionally, the shared architecture in GBT-based actor-critic methods significantly reduces memory and computational requirements, making it more efficient for solving complex, high-dimensional RL tasks with millions of interactions. Overall, the practical benefits of using GBT in reinforcement learning compared to neural networks include improved performance in tasks involving structured and categorical data, enhanced interpretability, seamless integration with RL optimization packages, efficient handling of non-stationary distributions, and reduced memory and computational requirements through shared architectures.
How were the experiments conducted to evaluate the performance of GBRL in comparison to neural network-based implementations in various reinforcement learning algorithms?
The experiments to evaluate the performance of GBRL in comparison to neural network-based implementations in various reinforcement learning algorithms were conducted across classic environments, high-dimensional vectorized environments, and categorical environments. In classic environments, agents were trained for 1M steps using continuous control and Box2D environments from GIM, with results normalized for comparison. In high-dimensional vectorized environments like football and Atari RAM, agents were trained for 10 million time steps, showcasing GBRL's superior performance in structured data environments like football and underperformance in unstructured environments like Atari RAM. In categorical environments such as the mini-grid domain, agents were trained for 10M time steps, demonstrating GBRL's significant advantage over NN in tasks requiring object interaction. Additionally, the experiments compared GBRL with traditional GBT libraries like CatBoost and XGBoost in the CartPole v1 environment, showing that while standard GBT libraries struggled, GBRL efficiently solved the task and remained competitive with NN implementations. The experiments also evaluated the benefits of the shared AC architecture by training GBRL on mini-grid environments with shared and non-shared architectures, highlighting the reduced GPU memory consumption and increased training FPS with the shared structure. Overall, the experiments were meticulously designed to showcase GBRL's strengths in handling structured and categorical data in RL tasks, emphasizing its potential advantages over nitrogen mononitride-based implementations in specific environments.
What were the main results achieved with GBRL in different types of RL environments, such as classic environments, high-dimensional vectorized environments, and categorical environments?
The main results achieved with GBRL in different types of RL environments are as follows. 1. In classic environments, GBRL showed similar performance to nitrogen mononitride-based training when optimized using A2C. However, in specific environments like mountain car, GBRL outperformed NN with all AC methods, while in pendulum, NN performed better. 2. In high-dimensional vectorized environments like the football domain, where features are manually constructed and represent identifiable information, GBRL greatly outperformed NN across most environments. However, in the Atari RAM domain, which provides unstructured data, GBRL generally underperformed compared to NN except for AWR. 3. In categorical environments like the mini-grid domain, which require handling structured data, GBRL outperformed or performed on par with NN in most tasks. Specifically, GBRL significantly outperformed NN, showcasing its strength in problems characterized by structured data. Overall, GBRL demonstrated strong performance in environments where structured and categorical data are prevalent, showcasing its potential advantages over nitrogen mononitride-based approaches in these specific types of RL environments.
What are the limitations or challenges faced by gradient boosting reinforcement learning, GBRL, as discussed in the paper?
The limitations or challenges faced by gradient boosting reinforcement learning, GBRL, as discussed in the paper, include the non-stationary state distribution and online learning nature of RL, causing varying gradients in magnitude and direction, which can destabilize training or lead to catastrophic forgetting. Additionally, feedback in RL is provided through interactions with the environment and is not available a priori, unlike in supervised learning settings where targets are predefined. Traditional GBT libraries rely on features like GOS, categorical feature encoding, early stopping signals, pruning methods, and strategies for online learning, which may not be suitable for RL tasks. GBRL addresses these challenges by employing tools from both NN and GBT literature, such as batch learning, to update the ensemble at each boosting iteration. This approach helps handle non-stationary distributions, improve stability, and focus on different parts of the state space to accumulate beneficial gradient directions and minimize detrimental ones. Furthermore, GBRL fits gradients directly to optimize objectives, whereas traditional GBT methods require targets and workarounds to effectively utilize gradients. The paper also highlights the need for appropriate adaptations to handle the unique characteristics of RL environments, such as non-stationarity and online learning, to fully leverage the potential of GBT in reinforcement learning.